Okay, in this video we will be going into the Doppler effect with a little more detail. Let's watch this. So hopefully you saw or you heard the frequency changing. High frequency as it approaches, low frequency as it's going away from you, the listener. So we have four different situations. Here they are. One situation, so here's you, and I drew your ears extra big because you're the listener. So in this situation, in the top two, excuse me, you are stationary. You don't move. The source of sound is coming towards you in this situation. And in this situation, the source of sound is moving away from you. In our third situation, the source of sound is stationary, so the guitar is emitting some frequency and it doesn't move, yet you on your skateboard are approaching the source of sound. And here, in the fourth situation, you are moving away from or receding from the source of sound. So what I'd like you to think about is, in each of these situations, the source of sound emits some frequency, F. And we're wondering what you, as the listener, will hear. And in each of the situations, you will hear a frequency that is different from the one emitted by the source of sound. So give it some thought. Would you hear a higher or lower frequency in each of these situations? Okay, so if you need more time to think, put it on pause. Otherwise, let's talk about this. So, in this situation, in the top situation, you see how the sound waves are bunched up in front, meaning the listener, you, will hear more of them per time. So you would hear a higher frequency in this situation. In the bottom situation, notice how the sound waves going towards you are spaced out, meaning the wavelength is greater, meaning because sound is going to travel through air at the same speed in each of these situations. If the wavelength is greater, you're going to hear less of them per time, and so you would hear a lower frequency. Frequency is number of waves per second that you hear. So, down here, we have a stationary source of sound, and you, the listener, are moving towards it. Notice how you're going to pass by more waves per time. You therefore hear a higher frequency. And in the bottom situation, your multiple choice or matching skills would probably tell you that this is lower frequency, and that's correct. Lower frequency. So again, the sound waves are moving towards you, but if you're moving away from them, less of them are going to reach you per time, so you would hear a lower frequency. So that's all fine and dandy, and it kind of makes sense, but how can we describe that mathematically is the question. So, yes, we can calculate. So I know this formula looks a little crazy. We're going to talk about what these things all mean, but they basically apply to these four situations where we have you, the listener, and the source of sound either moving towards one another or away from one another. And it's different when it's the source of sound that's moving, and it's different when it's the listener that's moving. So first, let's talk about two extremes. So one extreme which we have discussed is this type of situation where the source of sound is moving, and pretend this car is emitting some frequency, and as the car goes faster and faster and faster, the sound waves get bunched up more and more and more and more and more. So when the source of sound is going the speed of sound, so for this top situation, source of sound equals speed of sound, what happens? Well, if the car were going the speed of sound, which would be quite remarkable, the sound waves would overlap and kaboom, we'd hear this large, it would resonate, we'd hear this large increase in amplitude, and it would be a sonic boom. the frequency, so imagine you have all these sound waves overlapping and overlapping and overlapping and overlapping. So when that passes by the listener and the listener hears this sonic boom, the listener is actually hearing sort of an infinite number of waves per time. So in this case, and it's a little weird to talk about infinity any time, but especially when we're talking about a frequency, but I'm just going to say it. So we have this source of sound going the speed of sound, sonic boom. It's kind of like the frequency has gone to infinity, because you hear all of these sound waves pass you at the same time, meaning zero time has elapsed between each of them. So that, if we look at the equation, well, let's just keep it at that. Okay, we'll look at the equation in a little bit. Second type of situation would be the extreme. Let's talk about this. So there is some stationary source of sound, and you, the listener, are on your skateboard. And let's say you've been practicing, so you skateboard real fast. So at some point, you could, so the listener, that's an S, the listener goes, you're skateboarding real fast, goes the speed of sound. So here you are conducting physics experiments on your skateboard, and you're pro. So what you're doing is there's a source of sound and you're listening to it, but you're going away at the speed of sound. So the sound waves move and you move away from it, and the sound waves move and you move away from it. So do you see how the sound waves would actually never reach you? So you wouldn't hear anything, which is or could be described as the frequency equals 0. Okay. So we have these two extremes, and this is going to help us when we think about the equation, because in math speak, right, if we get, I'll just leave it right there, if we get to talking about math, dividing by 0 is undefined, because we say the thing blows up, meaning you have a fraction, if the denominator is really small, the number is actually really big. So this is a situation where our frequency, if the denominator is 0, our frequency goes to infinity, and we get this sonic boom. So this is where the source of sound would be going the speed of sound, and we'd be subtracting them, so we'd get 0 in the denominator. And then this situation here, a fraction is equal to 0 when the numerator is 0. So if we have that the observer is actually going the speed of sound, and we subtract the 2, we get 0 in the numerator, so that would be this situation where the frequency heard is 0. Okay, so those were two extremes. They're pretty rare. But let's look at the formula and talk specifically about what all those variables mean. So, this formula applies to those four situations. So f prime, this is the frequency heard by listener, and f, this is the normal frequency, so the frequency produced by source of sound. So if you're hearing it, there's some source of sound, and what you hear due to the Doppler effect is going to be different. And so this equation, this plus or minus, and the numerator and denominator apply to two different situations. So if the listener is moving, we use the numerator, and if the source of sound is moving, we use the denominator. Source of sound moving. Okay, and I recommend knowing this, because you'll be plugging in, and let's say the listener's moving. You know, the denominator just stays the same as the velocity, speed of sound. This would be 0, but you're going to have whatever speed the listener is going, and you're going to have the speed of sound, and you're going to be wondering, should I add or subtract? And it's easy to get these confused. But what you know is that if the source of sound and you, the listener or observer, are going away from each other, you know that the frequency heard is going to be lower. So lower frequency. And if you, the listener, and the source of sound are moving towards one another, we know you're going to hear a higher frequency. So I think that that probably makes sense to you, and you can kind of just leave it at that and then think about it to figure out whether to add or subtract. But if that's not good enough, we can be specific and say the top is for towards. I like that. T and T, top for towards. And the bottom would be for moving away. Bottom for moving away from one another. So to use this formula, first you will be thinking, okay, is it the observer, the listener that's moving? In which case we're going to plug something in here, and this will stay the same, this will be 0. Or is it the source of sound that's moving, in which case this is 0. We just have speed of sound up top, and we'd plug something in here. And then are they moving towards one another, or are they moving away from one another? Knowing this, so you get an answer, and hopefully, if they're moving away from one another, the frequency you got should be lower than the original frequency, the frequency of the source of sound. And if the objects, meaning listener, source of sound, are moving towards one another, we should expect a higher frequency. Okay, so I'm going to stop there, and maybe we'll do some examples. Oh wait, I'm not going to stop there. Let's take a look at this. This is hilarious.
I don't care if anybody gets it. I'm going as the Doppler effect. Oh, it's time I have you. I can demonstrate. So what time does the costume parade start?
Parade?
Yeah, so Judge is going to give out prizes for best costume. Most frightening, most authentic, most accurate visualization of a scientific principle.
He is a classic physicist.